differential equations is because that's what I did my undergraduate research in, was solving differential equations. So, all right. So remind me, what is a differential equation?
An equation that's differentiable.
That has a
Not,
derivative.
that has a derivative in it. Okay, so not that I can take the derivative of it, because that's what it means to be differentiable, but that it has a derivative in there. Okay.
Oh wait, that's not
Okay. So when we are, like I said, we're not quite to actually solving it yet. We're going to look at our steps to actually solve. Today we're just going to look at checking to see if something is a solution or not. Okay. However, remind me, what did we say our solutions are going to look like?
It's gonna be a function.
It's going to be a function or an equation. So just like if I gave you, say, like a quadratic, and I said, hey, is x equals 4 a solution? You would plug that in and see if it gives you out 0 or whatever's on the other side. Yes? The only difference here is that instead of just plugging in a number into our differential equation, we have to plug in an equation into our differential equation in order to figure out if it works or not. So our first step is going to be to take the derivative. Potentially, we might also have to take derivatives if we have like a y double prime in there. And that's of our solution equation, or potential solution equation. Next up, we're going to plug into the differential equation. And then we're going to check if the result is true.
If it's not true, would you have to restart stuff?
So it depends on how the question is worded. So like we're going to see two different things. We're going to see one, if it says verify that this equation is the solution, then yes, you would need to restart because they're not going to lie to you. It's not going to be like verify it, just kidding, it's not really, right? That means that you did something wrong somewhere. If it says, is this equation a solution, then your answer could be no. So then your answer would just be no, and you don't have to start over. Does that make sense? Yeah. But you do see the verify ones quite often. I think we've looked at one kind of like that on our AP practice. You'll see these on the AP test sometimes, because what's nice about those is if like step 1 is verify that this is a solution, and then like step 2 is based off of the solution, that way then you can do the rest of it without having to like solve for something on the first one. Because like if you solve for it incorrectly, then that messes up everything else on them. But if the first step is verify, they technically already like gave you the answer. You're just showing that that really is an answer. But even if you can't show that it's an answer, you still have the answer to then do your other parts with. So that's why we'll look at some where you're just verifying. All right. So we have, is y equals sine of x a solution of y double prime minus y equals 0? And then what about y equals 4e to the negative x? So which one of those is my differential equation? The second one, the one with the y double prime? Because that's the only one that has a derivative in it. So that's what makes it a differential equation, okay? Which means that the other two are my potential solution equations. Yes? Are you okay with that? So let's look at the first one. We're looking at y equals sine of x. What do we want to do first?
Derive it twice?
Correct. Y.
Because one of the numbers involved is y double prime, so
Agreed.
it makes sense to find that.
Well, but actually need the first derivative for this particular differential equation? No, but we still have to find it in order to be able to find our second. So what is the derivative of sine of x?
For sine of x?
Okay. Do we need a plus c here?
No.
No,
Why not?
we're not taking the integral.
Oh, we're not taking the antiderivative. I'm just taking the derivative. Yes. But we do need to make sure that we're keeping those straight, right? So like derivatives do not get c values. Antiderivatives do get c values, even though some of y'all forget to put them on your test.
We don't need to call.
Yeah, Carr felt real left out on your last test. So,
We don't like them.
well, too bad. He's that weird, creepy dude that always needs to show up whether you like him or not. So,
Easy to forget about.
all right. So, what do we need to do next? We said take our second derivative. What is the derivative of cosine of x?
Negative sine of x.
All right. And then we're just plugging those values into our equation. So, our equation is y double prime minus y equals 0. So we said our y double prime is negative sine of x. Our original y is just sine of x. And I need that to equal 0. Okay? What do I get on the left-hand side?
Negative 2 sine of x.
Does that equal 0?
I mean, it depends on the x value, but no.
No, so like again, we are, it has to be true for everything.
Yeah,
So
but
it is not true for all. Therefore, what is my answer?
No.
No, it's not a solution.
Oh, so if it's not true for all values?
Everything. Correct.
So then we don't do the same part?
Huh?
Then we don't do the what about y?
Well, we are.
Oh, okay.
So that's why I drew a line, because that's like a separate thing. Alright, so now this time we're starting with our y equals 4e to the negative x. What is our derivative of 4e to the negative x?
negative 4 e to the negative x.
Why is it negative?
Because when you derive x and multiply it out, it comes out as negative 1.
Question? Yeah, we gotta use our chain rule. So our derivative of e to the x is just e to the x. However, our exponent has a negative x, so we have to use our chain rule to take the derivative of the inside stuff. The derivative of negative x is negative 1, which I think is what you were trying to get at.
Yeah. I just saw you frowning and then I got confused and I'm like,
Your wording was a little odd, so that's why I was clarifying. So if I take the second derivative, what are we gonna get?
4e to the negative x.
Yeah. Do we remember what our cosines and our, or like our trig function, sines and cosines, and our e to the x's are called? They have a fancy name. They're called our transcendental functions. Basically, your transcendental functions are the functions that don't go away when I take the derivative of them, right? Because like if I just have like 4x cubed plus x minus 3, yes, that eventually, if I took enough derivatives, I would get to 0, right? Versus like e to the x, sines and cosines, our natural log. If I kept taking derivatives of those, they do not go away. So, which is why a lot of times you will see differential equations that have sines, cosines, and e's in them, because they are more interesting than if you just take derivatives of polynomials. So again, we're checking to see now if this works. So y double prime is 4e to the negative x. Y was 4e to the negative x. Does that give me 0?
Yes.
yes.
He's happy. So our answer this time is
Yes.
yes.
Says Jones.
Sure. It's very square nose. Or they could be glasses, I guess. I don't know.
It could be like an elephant or something.
Alright, let's look at another one. So it says given the equation, verify the general solution. So if it tells us to verify this time, should it work?
Yes.
Yes.
Yeah. We did something wrong if we get no, because it should work. Okay. Then find the particular solution when x equals negative 3 and y equals 2 as an initial condition. So what about my my given equation makes it a general solution. Or what is different about this solution than my previous solution?
There's a
Our other
C.
one had x's too.
Transcendental?
It's also not transcendental, that's true.
There's a C.
Okay, what does C stand for?
Carl.
Carl, or our
Constant.
constant.
Oh.
So this one has a constant in it. So if I have something that has just a C value in it, that is going to be our general solution. Meaning that I could pick an infinite number of C values and all of those would work. Now, in order for us to find a particular solution, they have to give us some values that we then plug in. Kind of like on our slope fields where we plotted one point to graph it. Basically here, my x equals -3, y equals 2 is my 1 point. Yes, yes.
Is it Carl a coefficient in this one?
It is. And we will end up with some of those. It's not always plus C
Oh.
whenever we start taking antiderivatives in this case. So, here, again, I need just the first derivative. What's our first derivative? 3cx squared. And that's all we have to take this time. So if I have x's in my differential equation, they just stay x's. And then for my y, I plug in the original equation this time. So multiplying, we get 3cx squared times x gives us x cubed minus 3cx cubed. Does that give us 0?
Yes.
Yeah. So we verified it. Yay. Then the next step is it asks us to find the particular C value. Where am I plugging those values back into?
If it says initial condition, do we want to plug into an original equation or no?
It is the original. It's not because it says initial condition. What value does it give us?
X values.
Gives us an x value and it gives us a
Y value.
y value. Does my derivative have a y value in it? No. So if they wanted us to plug it into our derivative, they would have needed to give us
Y prime.
y prime. Okay, so that still technically is called an initial condition because it's a condition that allows us to solve for C. And we will have some where it actually has to give you an initial condition for both your y and your y prime, which we'll look at tomorrow. But if we plug in our y, we have 2. We plug in our x as -3. -3 cubed gives us
-27.
-27. And then to solve for C, we divide and get -2/27. Agreed? Is that my final answer? Yay, we're done? No, we said that our solutions for these are what? Equations, which means that we need to plug that back into our equation. I also had some people that forgot to do that on some of our tests. So remember, once I solve for my C, you have to plug it back in.